Welcome back. This is an Aleks training video on interpreting a reaction energy diagram. Okay, an energy diagram shows you with a picture what's happening to the energy that's stored in the bonds of the molecules. So if there's more energy stored in the bonds of the molecules in the reactants, it'll be higher up on the energy graph. Okay, if you can look on the left side of the graph, energy is getting bigger as it goes higher. So if there's more energy stored in the bonds of the reactants, then it will be higher on the left and lower on the right. That means there's less energy stored in the bonds, and that energy that's left over has to go somewhere and it goes out. That's called exothermic. The thermic is the energy, heat energy, exo out. Okay, so you're going to have something like this is going to be exothermic. Let's look at the picture. You're going to have a certain amount. This is your reactants. The reactants will always be on the left. The products will always be on the right on an energy diagram. In this case, you've got it higher up here at the beginning, lower down here. That means the energy stored in the bonds here are higher than the energy stored in the bonds here. Okay, so the enthalpy here, the energy, is going to be, so C plus D, the energy is going to be at 250. So this is H will equal 250. Okay, this is the products. The enthalpy or energy at the beginning is going to be 300. This is kilojoules per mole. So when I take products minus reactants, okay, so when I say delta H products minus delta H reactants, I'm going to get negative 50 kilojoules per mole. Okay, this negative is going to tell you that it's exothermic. The heat is coming out. You're going to get a negative delta H, then it's going to go away, right? So if it's backwards, for instance, if you had something like this to where you had less energy at the beginning and more energy at the end, you could say that this number, let's say it's 100 minus this number 25, is going to be positive. So if delta H is positive, that's energy went into it. There's more energy at the end than there was at the beginning. The energy came from the environment, got sucked right out of the air. The energy of the molecules in the air gave it that energy, and so you would have a positive delta H. Okay, so your first question is asking you, is this endothermic or exothermic? Well, it's losing energy. So it's lower energy at the end, so it's going to be exothermic. That'll be your first question. Now the next two are pretty simple also. Can you determine the activation energy? So let me put up a definition of activation energy. So the activation energy is the energy that you have to put into something in order to get something out. All right, and normally you want a good investment. You want to invest a little bit and get a lot. So if you look at the energy diagram here on the left, I've got 300 kilojoules per mole energy inside the bonds and only 250 on the left or on the right. So I can get 50 kilojoules of energy out of it, but I have to put a little bit into it. So I have to invest some energy because before it goes down, it doesn't just go straight down from here to here. I have to add some energy, and then if I add some energy, I get more than I put in plus more out. That's the activation energy. So the second thing here says the height of the energy barrier from reactants to products. Well, from here's reactants, here's products, this is the barrier. So from this level here to here, that's the barrier. So I simply go from this side and to the top, how far is that? So it goes from 300 to 400, right? So the second question is, can you determine its activation energy? The answer is yes, you can. And how much activation energy is it? Well, it's 100 kilojoules per mole. 100, because it went from 300 to 400. Okay, now you're going to get more out. You put 100 in, you're going to get 150 back. So you'll get a net gain of 50 kilojoules per mole energy, but you have to put in activation energy in. That's the reason why you have Bunsen burners in a chemistry lab. You want to put two chemicals in a test tube. You may need to give it a little bit of energy to make them bump into each other. And then once you give them the energy, they'll react, and that reaction may let off more heat than before. You're going to have to start a fire. You can't just, you'll have to give it a little bit of energy to start the fire. You couldn't put a log, you can't start a log with a match. You would have to put a log on something hot enough to ignite that entire log, and you add a little bit of energy, you'll get energy out of the log. It's the same thing. The last one is, can you determine the activation of energy of the reverse reaction? So they're imagining a reaction now where CD is your reactants and AB is your products. So think of this backwards. Go backwards in your mind. Think of this on the left and this on the right, right? First of all, it's endothermic, right? Because this has less energy, more energy. So energy would have to come in order to make this to be the products. Okay, they didn't ask that question. They just said, what's your activation energy? And the activation energy is the height of the energy barrier from reactants to products. So if I'm going backwards, this is reactants, this is products, this is now the barrier. Okay, this is the barrier. I have to go 150 high before this would actually happen. Okay, so some reactions will go in one direction very easily, but not in another direction, because the likelihood of putting this much energy into something is not very much. You can't, it's harder to do. So it's harder to throw a rock off the top of a building than it is to throw a rock onto a building. It's the same thing. The chances, it's not impossible, but the chances are lower to go this way than to go this way. Okay, it's more likely to go from here to here. All right, so how much is it? Well, I start here, and I'm at 250 kilojoules per mole, and this is 400. That means it's 150, so yes, the answer would be yes, and it's going to be 150 kilojoules per mole reaction. Okay.